First up, we run the program scan on the computer in order to access all the wavelengths. You need to scan across all wavelengths to find the maximum wavelength at max absorbance. The wavelength in which the absorbance is at the maximum value is also known as the lambda max. Therefore, scanning at a specific wavelength allows you to compare the concentration of a certain sample to make a curve. And here's the curve that we are given. And because different samples might absorb best at different wavelengths, it is important to have a wavelength that will take all substances into consideration. Therefore, we chose the maximum value and took it and inserted it into our simple reads program. Once we have used the scan program to use access to all wavelengths and to find the wavelength at max absorbance, we then use simple reads. Within this program, we can utilize Beer's law. Beer's law demonstrates that absorbance is proportional to the molar absorptivity and the concentration of the solute. Absorbance and concentration have a direct relationship, which means that since absorbance increases, the concentration also increases. Likewise, when the absorbance decreases, the concentration also decreases. Therefore, Beer's law can be interpreted by A is equal to epsilon times L times C. However, Beer's law can also be represented with more familiar equation, y equals mx plus b, where y represents the absorbance, m represents the slope of the calibration curve, x represents the concentration, and b can be represented as 0, because if the concentration is 0, then the absorbance will also be 0.
To make our stock solution, we dissolved 0.127 grams of copper sulfate pentahydrate in water. To make the first dilution, we added 9.61 milliliters of the stock solution in a 25 milliliter volumetric flask. We then added water until the meniscus hit the 25 milliliter mark. We repeated the process by performing a serial dilution. In total, we had 6 cuvettes, 3 samples with known concentrations, the stock, an unknown, and our blank solution, which was water.
After using the spectrophotometer to find the absorbances, a calibration curve can be plotted. The slope of the curve is represented through m by plugging in the known absorbance found through the spectrophotometer, and the slope given by the curve x, or the concentration, can be solved for. Water is used to zero out the absorbance of other substances so that it does not interfere with the measurement of absorbance of the analyte. This is done to make sure that the machine is zero, thus ensuring the most accurate reading of the absorbance values.